So yeah, I'm Catherine. I joined the AI engineering team as an intern just in January. And yeah, let me. Oh, and I'm a student at UofT. I'm an undergrad student in engineering science robotics. Yeah, so today I'll be talking about the work that I've done so far in my internship. And yeah, just jump straight into it. So over the course of this internship, I've worked on kind of two main components. The first is working on the robotics workshops with the Dynamic Systems Lab for Vector sponsors. And the second is working with the Safe Control Gym, which is a safe reinforcement learning benchmarking gym provided again by the Dynamic Systems Lab from UofT. For the robotics workshops, I'll first just give an overview of what those are really about. So these workshops were meant to be providing knowledge transfer of the concepts in autonomous navigation and safe learning, so to robotics areas, to the broader use cases of Vector sponsors. So the sponsors that joined for these workshops aren't generally robotics based, and that's exactly what we wanted to do, is provide the thorough background for these concepts and have them be able to apply to more unique and interesting use cases beyond those specifically in robotics. And this is with the Dynamic Systems Lab from UTIUS at UofT, which is led by Professor Angela Schoellig. So for these workshops, I helped a lot with the project management team. And so with the project management team, I helped complete framing for the workshop, a concepts guide, and did use case research. And these three things were to really help understand how we would present the workshop to sponsors to onboard them and have them interact with the workshop material. In addition, I have met with sponsors to help discuss their use cases and help frame how they are going to be going through the workshop, as well as offering continual support technically and on the project management side with the project management team. So some specific things that I've helped with for these workshops. For the safe control workshop, I helped develop a Docker image that provides an environment to work with the safe control gym on Vector's cluster. So Vector's cluster didn't have a lot of the dependencies that are required for this repository. And so we helped containerize that and have it be able to be used on the cluster without having to explicitly have those dependencies. And this also just helped us get familiar with the future working with Docker images on the cluster and providing these containerized environments. Along with that Docker image, I created a guide to work with for workshop and bootcamp participants to work on the cluster and get started. So initially, it was people who are running workshops and boot camps would write up a specific set of instructions. But what I've done is provided a condensed guide from the computing wiki that can be used across all boot camps and workshops. In addition, I wrote up instructions specifically for the robotics workshops that provided instructions relevant for just those workshops. And so in the future, we hope to expand upon the guide that was created so that it can be used as a basis for other workshops and boot camps at Vector in the future. Now I'm going to talk a bit about kind of the main project that I've been working on in addition to the workshops, which is the work that I've done with the Safe Control Gym. So the Safe Control Gym, as I mentioned before, is a safe reinforcement learning benchmarking gym. And it provides the ability to test the safety of different control approaches that are implemented. And it does this by providing lots of different tools that allow you to test different aspects of safety. So they have the ability to define constraints on state and input that can be tested for violations throughout training and evaluation. And this helps you better understand your control approach's ability to satisfy constraints. As well, you can implement different disturbances on input, observations, and dynamics. And this helps test the robustness of the control approach that you are implementing. As well, it provides different baseline implementations of classic control approaches as well as reinforcement learning and learned approaches, so that you can compare any control approach that you are implementing to useful baselines. And up in the corner is just an example of a visualization provided by the gym. So they have different agents available. There's 3 different agents actually. So there's the classic cart pole example, and there's also the quad rotor in 1 dimensions and 2 dimensions. And here you can see a 2-dimensional quad rotor agent example. So the first thing I did with this gym was a code review. So when I started working with the gym, there was no walkthrough or guide to working with the repository. There was only a README that provided some initial instructions for installation and some predefined experiments, but it was really not trivial to get started with custom experiments. So what I did was completed a review and just continued to go through the repository and created a walkthrough of setting up experiments, how to configure different experiments, review of the controller types, how to do logging, and in general other functionalities of the repository and how to set those up. In addition to this tutorial or walkthrough, I provided many different code contributions, and this was bug fixes and enhancements, including things like providing GPU compatibility for the repository. And so these contributions were mainly to improve robustness to user input in the case of configuration, improve code readability in cases where things were not clear, and in general, reduce spin up time for new users to the repository, as this is an open source repository. In addition to this code review, I've been completing a series of experiments on the repository to help fill out some of the results that were provided in the paper that was released along with the repository. In that paper, they break down safety into 2 sections, which is constraint satisfaction and robustness. In the paper, they discuss more thoroughly constraint satisfaction, but there's a lack of results on the robustness aspect of the baselines that they have implemented in the repository. And they only look at white noise disturbances applied to actions and variation of pole length in the case of the cart pole agent. But there's lots of other capabilities that the repository has that would be valuable to look at to kind of define and analyze the robustness of the different controllers available in the repository. So that was my goal of these different experiments. So here's a kind of review of the different aspects that I was looking at. So you can experiment with disturbances on dynamics, on states, and on input. And so I plan to do all of those to have a broad review of robustness and characterize it across all these different control approaches. They also provide different kinds of disturbances that have already been implemented. So white noise, impulse, and step disturbances were already implemented in the repository. In addition, I wanted to implement periodic disturbances to test the ability of controllers to deal with periodic disturbances over time. So I implemented sawtooth and triangle wave disturbances. And so the experiments that I looked at with these different aspects to explore were baselines. So just comparing the baseline performance of the controllers, as well as looking at comparisons on white noise, and then comparisons on more complex disturbances, and then finally implementing a more novel implementation of a robust control approach that has been described in research. So I just want to give some examples of the results that I've been getting through these benchmark experiments. There's quite a bit of results as there's a lot to look at, but the control approaches that I've been looking at in the repository include many of the reinforcement learning approaches. So PPO, RARL, RAP, soft actor critic. And this final approach is model predictive control, which is a classic control approach. So it's not it's not learned, but this particular implementation is with Gaussian processes. So it has an approximation of the dynamics that's learned before the controller is used. After I had the baselines, I wanted to look at the behavior of the controllers on white noise. In this case, I started with looking at white noise applied to the dynamics. And essentially what this is just an additional force that is applied to the top of the cart pole to see how it responds to disturbances from the environment. You can see here, I won't go too much into the details, but you can see here that in general, the reinforcement learning approaches have a much smoother behavior in comparison to the traditional or the classic control approach, which is the MPC. You can see here it's much more sporadic, which is one interesting insight from looking at this. I also wanted to compare the cost across these different, the evaluation cost across these different control approaches. So looking at this, it seems that the proximal policy optimization approach seems to fare the best across the widest variety of white noise standard deviations or sigmas. One interesting thing that I noticed is that when applying different levels of noise to in the experiments, there is a point at which it kind of reaches a point where it can't handle the noise anymore. And it's interesting that it doesn't follow a linear path and suddenly fails and because it becomes unstable. And you can see that here on the side, at some point stability is lost, which is a common issue with reinforcement learning. So the next thing I did, I wanted to see if providing white noise during training were to change the behavior of these different control approaches. And in general, it seems that actually introducing noise during training degrades the performance of the controllers. And this was similar across all the control approaches. And beyond a certain level, it can't even learn a policy that will reliably stabilize the cart pole. And so you can see, for example, here with RARL, the cost suddenly shoots up on a policy that has been trained with high levels of noise. After thoroughly exploring white noise examples, I wanted to look at the behavior on more complex disturbances. So this is the white noise. After that, I introduced periodic disturbances, including sawtooth and triangle waves. And it was interesting to see the different behaviors on these more complex disturbances. Yeah. So moving forward, I'm also going to be completing, compiling all of these results, but I'm also going to be implementing an additional newer robust approach. The one that I'm currently working on implementing is this one, which is robust hallucinated upper confidence reinforcement learning, which is a model-based reinforcement learning algorithm that promises to be more robust, and it'd be interesting to see in comparison to these other robust and just general reinforcement learning algorithms and classic approaches, how it fares. In addition to that, I'm working with Jacopo from the Dynamic Systems Lab to publish these results in a technical blog post and possibly report. Yeah.